Hey everyone, this is the first video for the week of April 13th through April 17th. I just want to show you the outline here. Hopefully you've opened this already. This is the last week of our third quarter. So if you're still working on older assignments, please finish this up. We've got just one assignment for every day this week. The term maps are not due this week. We'll continue circuits into our fourth quarter starting on the 20th. I also want to show you that if you haven't noticed, this outline will have everything linked, rather as much as I can. Some of the exit ticket forms are there. The only things that you have to go to Google Classroom for are going to be the docs that I have to make a copy for each of you for. But overall, just follow the outline. Of course, you're welcome to go ahead if you want to do more than one assignment on any given time. But follow the outline. As long as you've been doing that, you're in good shape. But I also made a new question sheet. This one is just more clear. I also wanted to kind of throw away all the older questions that don't pertain to circuits. So you have this in Classroom if you want to communicate and you think your question will help with others. Otherwise, email is always another way to reach out to me. Okay, so let's get back to the circuits. We want to talk about electric circuit equations here for the series circuits. But before we jump into that, we need to go back and review the Kirchhoff rules because those two rules dictate the equations. Only take us 30 seconds. The junction rule deals with current. It says that as electrons are carrying charge flowing through, that means that's a current, and it hits a junction. Well, that current is going to split 2, 3, 4 ways depending upon how many pathways we have available, and the total current is equal to the total current leaving the junction. Just means that charge is conserved. I just want to make sure you understand that current is the flow of electric charge. So the electrons carry charge. That's an intrinsic property of electrons. They don't lose charge even passing through the resistors. They keep their charge. So the junction rule just says the total current is still there. It's just in several pieces now. Kirchhoff's loop rule says that as you go around a loop of circuit, as that current flows in a loop from one terminal of the battery through to the other side, the voltage that it drops pushing through resistors is equal to the voltage it gets back through the battery. This rule is based off the conservation of energy, as you might remember, and it just says that you use voltage to push through resistors. That's what's used up, not current. The voltage drops through the resistor. That phrase just means you have some voltage here and a less voltage here because you've burned some going through. You burn some more. After you get through all the resistors in a loop, you're now at 0 volts, but you gain them back in the battery. That's what the loop rule says. The equations for series circuits just put those two rules and make equations out of them. So let's take a look. Let's say we've got a series circuit here, like the one in the picture. 4 resistors, a single loop. We can measure the voltage across any single resistor with a voltmeter. Again, that voltage of this one we might just call V1 since it's the first resistor that the current will encounter. We'll call the next one V2, etc. The current running through resistor 1 we'll call I number 1. The current running through resistor 2 is I number 2, and so forth. So here's just an example circuit. Let's talk about some actual equations to solve for these measurements. So if we're going to talk about current, well, we have to think about the junction rule. That's the one that deals with current. It says that if we have a junction, the current will split several ways, but in a series circuit, there are no junctions. There's only one pathway around the circuit possible. So if that's the case, no junctions, no current splitting, the current that comes out of the battery is the same current that passes through resistor 1, same as passes through resistor 2, etc., etc. So our equivalent current, the one again coming out of the battery, is equal to the currents going through every resistor. And hopefully you saw this in your series circuit investigation with the simulation at the end of last week. All the currents should have been equal no matter where you put the ammeter to measure. It's all the same. All right, but let's talk about voltage now. Same picture, same circuit. We'll consider the voltage. You gain voltage in the battery. You have to burn voltage going through resistors, and the total voltage you burn through a loop should equal the voltage you got back in the battery. Well, okay, so let's make that into a math equation. The equivalent voltage that you gain coming from a battery is shared between every resistor in that loop. Now, that doesn't mean it's split up evenly. Let's say this is 8 volts coming from the battery. It doesn't mean it's 2, 2, 2, and 2. It's going to be different based on the resistance values, but whatever the voltages through each of these 4 resistors are added together must equal the battery's voltage. That's what this equation down at the bottom says. It'll show up again in a moment after my bar goes away. But that's all it is. As many resistors as there are on the loop, add them all up. Their voltages added up should be the batteries. Okay, and the last measurement to talk about is the resistance of series circuits. If you combine those 2 equations I showed you, which are really just Kirchhoff's rules, with Ohm's law, remember Ohm's law is R of any component equals V over I, resistance equals voltage over current at any one spot. The only possible way resistance can add up in a series circuit is by just adding them all together. You've got, let's say, 4 resistors in a circuit. You add up all their resistance values, and they will equal the total resistance of that circuit. So I'll just show you a slide of all the equations together. Junction rule deals with current. They're all equal in series. Loop rule deals with voltage. Add up the voltages through the resistors to equal the battery's voltage in series. Add up the resistance values themselves of the resistors, and they equal the total resistance. Very simple, addition and subtraction. If you want to use Ohm's law, well, you can do that too. For any one resistor, its resistance multiplied by its current will be its voltage. And that works for any single component. All you have to be careful is to not mix around your values. If you're looking at a resistor and you label it resistor number 2, you can only multiply it by current number 2 to get voltage number 2. You're not going to solve for the battery's voltage by looking at resistor 2 and the current running through resistor number 2 necessarily. So just stick to one single spot in any equation. Every physics equation has that idea in the background. That's it for today's video. If you want to jump into the practice problems where I made charts for you, I'd like you to watch the next video and see an example problem first. But you can save that for tomorrow if you want to stick to the schedule I laid out in that outline. I'll see you in the next one.